Hi everyone! In this video series, what I'm going to do is explain the conservation of momentum. What I'm going to do is talk a little bit about what happens with momentum when you have an interaction of two objects. I'm also going to talk about the different types of collisions that we can experience as two objects interact or collide with one another. And then toward the end of the series, I'll show you numerous calculations of how to apply the conservation of momentum to different problems. And the final video series in this series will be a compilation of taking momentum into two dimensions. So how do we solve problems when the objects are not going linearly, they're going maybe in different directions. So the moral of the story is, through all the interactions that objects experience, they're going to conserve momentum. And this is a direct application of Newton's third law. When two objects actually interact, regardless of their size, we know from Newton's third law that when they interact or collide, for example, they are going to feel the same force. And when they separate off, they're going to have different accelerations based on their mass, or different, different motions from that. So that is the basic idea here, and that's one big law. Now, we call it conservation because whatever we start with in the initial conditions, we're going to find the total value is going to be the same at the end of those conditions right there. So this is a conservation law, which means that it governs all interactions, and we have to follow these laws. For example, when two things interact, we're not going to see something just automatically speed up with no extra external force. Now, we kind of understand that and know that through experience. You know that if you run into something that you're not going to just magically get more, more speed from that. But this is using physics to explain that. So again, we're looking at an object's, what happened to an object's momentum. Where does it go? Well, it's some of it, in its essence, what you're going to do is you're going to be transferring it. Some momentum will be, for example, we have two cars right here, and we have them going to be interacting in this case. So what we can have is the car in A and car in B have their own momenta, but then when they interact, A and B will transfer some of their momentum, but the way they transfer it is conserved through the conservation laws. So basically, in the absence of an external force, the momentum of a system is conserved. So I can write this mathematically two ways. So first way, we're going to use this one most often, is right here, is that the total initial momentum of the system has to equal the total momentum final of the system, which is essentially what this says as well, that the change of momentum of the system is zero. In other words, the two values are the same. So what do we mean by an external force? So in other words, there are two main examples of this. First, our biggest one is friction. Now, momentum will be conserved, so in other words, when two objects collide, they'll bounce off each other, and in our perfect scenarios, which are going to be 90% of our problems, the objects will keep their velocity as they move along. However, in real life, what happens is when two things interact, they'll start off with their initial velocity, but they'll start to slow down, and that's due to friction. So technically, momentum's being lost because momentum is a factor of mass and velocity. So yes, in real life systems, momentum's not conserved. But if we do not include friction, then it will be conserved. And we'll notice this in lab as well. When we make these calculations, we'll see the general idea is there, but a little flaw will be in our measurements due to the fact that we're not looking at our external forces. Another example of an external force could be a push, So let me just be really silly here because this is an unlikely scenario, or actually no, a real life scenario. I have one right now. Is imagine if you're driving in your car. Now, anytime we solve momentum problems, we assume the velocity is constant. But if we were driving in our car and we step on that gas pedal, which you shouldn't do during a collision, but let's say you got scared, and that actually kind of happens sometimes, is that you instead of the brake, you might hit the gas. Well, you're adding a force there because pushing on that gas gives you a force. So when the system, when you actually collide, that gas pedal acts as an external force, so our numbers will not match up. So in other words, the law is the momentum is not considered or conserved in that system. So that's what it means to have an external force. So what we do and talk about in physics is when things do interact, this force, the one they actually collide with, is an internal force because it's part of our system. It's part of our two objects. This is not the external force of the system. External literally means from the outside of the system. So what it turns out is we're going to ignore friction, unless, of course, otherwise specified, because otherwise that will interact with our conservation law. And the momentum's constant. It's not changing. So we can rewrite this if there is an external force the way I derived it in class, basically saying that if you take the change of momentum and redefine it in terms of a force right here, and this is an impulse really, is that we can define a change of momentum as related to the impulse. So for example, one of the questions we've done in class is the impulse of an airbag. Well, that airbag provides an external force to the system, which slows it down, which is why momentum is not conserved in that case. So these are all related, even though I'm treating them as completely separate things. So this is our way to actually write this as a force. So in the unlikely case that you might have to solve for this, this is how you can find the external force of your system. Okay, so here are some quick examples. Is it conserved or not? Cars accelerating toward one another. No, it's not conserved because we have an external force. A bullet embedded in a block. Although in reality there's a little loss, we're going to treat this as a conserved system because nothing else is involved there. It's just going to be a block and a bullet. And even though it's embedded or inside the bullet, the block, this is going to be considered conserved. A block sliding down a rough incline, not conserved because rough implies friction. Ice skater standing in the middle of ice throws her gloves. Yep. There's no external force, and the fact that the ice skater is on, the person's on ice, we assume no friction. And two billiard balls collide? Sure. That will be a conservation. Now, of course, billiard's on felt, but that's okay. In essence, we find that actually billiard balls, in terms of how you play billiards, is hugely related to the conservation of momentum. So that's conserved as well. So, what we can do is we can write our relationship of conservation of momentum in a few different ways depending on the system, but the way I have it written right now, we say that the total momentum initial has to equal the total momentum final. So, if you have two objects, which 90% of the time you will, it's going to be momentum of the first object initial plus momentum of the second object initial equals momentum of the first object final plus momentum of the second object final. And then, of course, we can expand that out in terms of their momenta. So let me just write this out because I think it always helps to see it instead of just talk about it conceptually. Let me go over to here. Okay, so the sum of the, change color, sum of the momentum initial equals the sum of the momentum final. So the momentum of the first object initial plus the momentum of the second object initial must equal the momentum of the first object final plus the momentum of the second object final. So these indices, 1s and 2s, represents how many objects. Now, most of the time you'll be dealing with two objects, but these can go on forever, 2, 3, 4, 5, as many as you need. And then remember, momentum itself is mv. So what we can do is m1v1i plus m2v2i equals m1v1f plus m2v2f. So a couple things I hope you notice that these m's, m1 and m1, are the same, so because it's going to be the same object. And this could be a car of m1 and a truck of m2, and their initial velocities, whatever they may be, m1, 0, m2i, and this is the before. I always draw a picture because I think you need to visualize what's happening here. And with words and the complexity of these problems, it's so hard to understand exactly what's going on unless you draw a picture. So then after would be the same mass car m1, but it can have a different velocity. Now, I'm just implying a velocity backwards, but that may not be true. But I'm doing that to show you that you can go forward, you can go backwards. It doesn't matter. This is still m2, and then m whatever this is, like that. So I think drawing a picture with the masses and the velocities will absolutely help you visualize how to write the equation and how to model the situation. But this is generally, and I put the word generally there because I'm going to actually change this a little bit, is how to approach conservation of momentum. Look at the two momentas, and you're going to write an expression to describe that system. So that's where, if you see this, that's where this comes from with the two objects here. So this is absolutely demonstrated very well with Newton's cradle, which is this. Now I'm not going to do it in the video, so hopefully I'll do it for you in class or with the air track system. So I'm going to leave that for a class demonstration. Or if you go online and you Google some of these, they'll show some really, really nice conservation of momentum demonstrations. But for now, I'm just going to skip over these. Maybe at the end of the video I can lead you to some links to see these demonstrations on your own. They're very worthwhile to see because I think when you see the demonstration that you'll understand it way better. So because there are many different types of collisions or things that can happen during a collision, we can organize them into three types. So our three types of collisions that occur are the following. The first one's called a perfectly elastic collision. Now, elastic just means the objects do not stick together. They literally, I use the word bounce, but they don't have to bounce off each other. They just have to not stick. That's the condition for elastic, is non-sticking. So they can actually come together and bounce off like this. They could be moving the same way and hit each other like that. So it doesn't mean a head-on collision. It just means that they don't stick. Now, the word that refers to perfectly refers to the fact that there is no energy loss. So, in other words, when two objects collide, they transmit all of their energy and their momentum all of it. So, when does that happen? It's actually a special case. The best cases are hard objects, so like Newton's cradle are very hard metal spheres. So you'll see that in that case. Now, not all problems will say bumper cars, but I put it here because sometimes in problems it says a perfectly elastic collision in these bumper cars, or the car, but notice that actually bumper cars can actually technically deform a little bit. But the thing is, you don't want the object to deform. You want it to transfer all of its energy. So billiard balls is another great example. And of course, as always, go with the context of the problem. Unless you're solving for collision type, it should clearly tell you what kind of collision it is, because you need that information. So in elastic collision, sometimes known as partially elastic collision, these again is a non-sticking problem. When the two interact, they don't stay together. But here's the difference, is that there's energy loss, and that's due to the objects deforming. So what does that mean? It means that when the objects collide, there's some energy transfer to smashing, okay? There's some heat involved in that, and there's energy loss. And if there's energy loss, you can have velocity loss. Sorry. Hey. There you go. I'll stop touching that. So some big examples are like two football players. Realistically, most collisions follow this. A tennis ball and a racket. I'll show you a visual in a moment of something deforming, but most objects will lose energy during collisions. Once again, go to the context of the problem. It either has to specifically tell you it's partially elastic, or that's, of course, something you're solving for. But that's the only difference between these two, is one is no energy loss for perfect, and energy loss for regular or partial. The last one is called perfectly inelastic collision. Now, inelastic is the opposite of elastic, which means sticking. So these things actually, when they collide, they come together and move as one afterward. That's the implication of an inelastic collision. So it doesn't have to be a start, separate and collide and move. It could be a move and then release. So it could be either of those cases. And because you're combining, just like with the partially elastic, when you deform, you lose energy with that. So there's definitely going to be an energy loss during these problems. So this is when you read to the context of the problem when the cars collide and they lock bumpers, or you have a bullet embedded in a block, or a big fish eats a small fish. These are all your keywords for perfectly inelastic collisions. This is exactly what I just said, but this is the equation that models it, which is exactly what we had earlier. And then to find energy or energy loss, you're going to look at the total energy initial and look at the total energy final and compare them. If they are equal, then energy is conserved. And notice that I specified kinetic energy because we're moving in these cases. We're not moving up or down hills, we're on a level surface. So notice that we're comparing initial kinetic energies and final kinetic energies. So what happens is these will correlate directly to these velocities right here. So the VI1 here is the same VI1 here. So this is a perfectly elastic collision because if we look at the total momentum before and after, we'll find that it's the same. And then if we looked at the velocities, we would find that they perfectly match. But the thing that I want you to really pay attention to right now is the fact that they don't stick together, which makes it elastic. What makes it perfectly elastic is that their energy is conserved. So I'm not going to calculate it. I hope you just take my word for it. But if you did calculate, you'll find that these velocities perfectly match. So because the objects bounce off in an elastic collision or partially elastic collision, we still have a bounce-off equation for this, which means that the initial velocity and the final velocity of this case is going to be the initial velocity and final velocity of this case. So it's the same equation as before, but what makes it different is the fact that if you calculate the sum of the initial kinetic energies, it's not going to equal the sum of the final kinetic energies. Of course, in a lab setting, these numbers will be comparable. They won't be exact due to experimental error, especially if you have friction involved. But if energy is not conserved, these numbers will be drastically different. And if you look here, this is a slow motion, a high-speed camera capturing how much a tennis ball actually deforms during its collision with the tennis racket, which is surprising because we don't catch it because it's too fast, but this would be a partially elastic collision because of this case. And lastly, inelastic collisions, they're the collisions that stick together and combine in the end. So here's a case. You have one block moving toward a second block, but afterward they move as one block later. That's what makes it an inelastic collision. Notice the way I model this situation. I have the initial momentum of 1, the initial momentum of 2. This is all the before. But notice the after. This acts as one object, so I actually add the two masses. And then, since they move together, they're going to share the same velocity. So that's why we write it like this. Now, they don't have this on the AP Physics equation sheet, but notice that you can build it based on what you see. This is separate, so they will have separate momenta. This is together, so they will have one mass and one velocity. So use your, use the diagrams and pictures to write the equations or help you write them out. And again, there is huge energy loss in this case due to mostly heat because of the collision like that. And energy will not be conserved. So if you find the total kinetic energy before of this system, it will not match the ending system like that. Now I wrote it like this, but you can actually find the change in kinetic energy. Let me just write that down so you get a visual. Oops. Sure. So I could write that the change of kinetic energy is the final energy minus the initial, right? The total. Actually, it should be the total. And if energy is conserved, then KE will be 0, right, for conserved. And when the change in kinetic energy is not 0, it's not conserved. This is just another way of writing exactly what I have down here. So another way to solve the same type of problem. So the main point of this animation is to show you is give you a visual of what an inelastic collision looks like. So notice that they stick together and move as one afterward. And if you spend a couple minutes just watching it a couple times, you'll find that momentum's conserved. The total momentum before is the total momentum after. Okay, so I'm going to stop this video here because we just talked about all the conceptual stuff. In the next couple of videos, what I'm going to do is solve each one of these problems so you can have many examples of how to apply conservation of momentum. Oops. Just gotta stop the video now.